I went to an F1 team to see how F1 suspension works and the incredible engineering behind it. Alpine F1 gave me special access to their 2022 F1 car, and I spoke to their chassis systems manager to explain more. Before we get into the details, let's follow how movement flows through an F1 car's suspension. When an F1 car goes down a straight, downforce builds with speed. The wings and floor get sucked towards the ground. The load travels through the suspension and eventually into the tyres, giving the driver some lovely grip. So when at high speed in a straight line, the chassis moves down, or the wheels move up, and in turn, both push rods move, pushing upward and inward. This movement pivots through something called the rocker, basically a metal part that connects to the torsion bars, the dampers, the heave spring, and the anti-roll bar. So let's start with the torsion bar, which is simply a metal tube, with one end connected statically to the tub and the other end moving with the rocker. It's a simple version of a coil spring. The rocker is also connected to the dampers, which help control the up and down movement of the car. If it didn't have dampers, the whole car would be bouncing all over the place. Then there's the heave spring. This is for controlling the car when it has a loss of aero load and isn't turning. On a straight, both wheels move up together and both push rods move upwards too. As the rockers rotate, the heave spring compresses. Now, this spring is slightly unusual in the fact that there's normally a gap before the spring comes into play, and when they do, they're very strong. Once the heave spring is engaged, the chassis of the car can't move down any further, stopping it from being pushed too low into the ground. But in the corners, it's different. As the car leans, one wheel goes up while the other goes down. Now those rockers are moving in opposite directions, so the heave spring isn't really involved. But that's where the roll bar comes in. It's another metal tube that runs down the center of the main torsion bar and connects both sides of the suspension. When a car leans in the corner, the anti-roll bar twists, fighting against that movement, and in turn helping the car to stay flatter and making it more stable and quicker through the corners. Okay, so that was a quick overview, and I'm going to show you the beauty of each individual part later. But first, why is suspension so important in F1? What does it actually do? Well, it's not just about going over curbs and bumps. As with many things in F1, a lot of it is actually about aerodynamics. From a pure aerodynamics perspective, you want the floor of an F1 car to maintain a perfect ride height at all times. If you can maintain a perfect gap between the ground and the car's floor, you're going to get the most downforce possible, and so go quicker around the corners. That's why in the 1990s, teams developed active suspension, a computer-controlled suspension that could keep the car's floor the perfect distance from the ground. It worked very well, but as you know, active suspension got very quickly banned. So now teams have to deal with a fundamental problem. You need the car to be able to move up and down to handle the bumps, but every time it does, you're changing that gap between the floor and the track, altering the amount of downforce. So why not get rid of the suspension entirely? Why not make everything rigid? Well, without suspension, you'd have a car that just bounced over every single bump, and it would be almost impossible to drive. Williams actually tried this in the 1980s, completely removing the springs and dampers from their F1 car. And while the aero in theory was better, the drivers just couldn't handle all the vibration going through their bodies.
The punishing, bumpy ride of the unsprung car is not popular with Jones. After 11 hours of work, they have a slightly faster but virtually undrivable car.
So suspension in F1 is all about finding that sweet spot, absorbing the bumps enough to keep the tyres properly in contact with the track, while keeping the floor's position as stable as possible for maximum downforce. So let's take a look at the beautiful parts that make up F1 suspension. And we'll start with the wishbones. F1 cars have double wishbone suspension, top and bottom wishbones connecting the wheels to the chassis.
All of these are made of carbon fibre all the way through, so we have used metallic in the past, but generally it's carbon fibre now.
And what you can actually see on the car isn't the structural part of the wishbone.
So this is a shroud. There's a structure inside here, so if you squash, you feel it goes hard inside. So there's a carbon structure within here, because then this gives us opportunity to change these shapes from an aerodynamic point of view.
Now, when the car's going in a straight line, these wishbones are dealing with pure vertical loads from all that downforce. But when the driver hits the brakes, everything changes.
Then when the car hits the brakes, effectively these are trying to turn themselves around. So all of those loads now are now trying to transfer down these wishbone legs to stop the wheels trying to spin round.
Turn into a corner and the forces shift again. These loads are so extreme and the wishbone's so important that engineers simulate everything with a safety factor of 1.8 times what they'd expect to see, because you just can't afford to get it wrong. And the wishbones are also packed with safety features and sensors. Hidden inside are 3 Xylon tethers, special straps that keep the wheels attached to the chassis during a crash.
A tether is a Kevlar bit of rope, so the idea being that obviously if in the event of an accident and all the wishbones are broken, the wheel doesn't detach from the car and head off somewhere where you really don't want it. It stays with the car.
And there's also wiring looms connecting sensors that measure everything from wheel speed to temperature, and even load cells that tell the engineers exactly how much force is going through each part of the suspension. So next, the push rods, the thing that transfers the forces from the wheel into the suspension. And while it might look simple, the engineering behind it is anything but. Teams can make these rods from either carbon fibre or metal, but here's where it gets interesting. It's not just about being light and strong. Sometimes, especially at the rear of the car where things get hot, engineers actually prefer metal.
Carbon's a fantastic material, but when it's quite hot and smelly around the back of here, sometimes you'll go to a metallic, and sometimes a metallic you can make slimmer. But it might be heavier, so it's that trade-off of which way you want to go. Kind of thing.
And if you look at the rear suspension, the rod is different.
So on this rear lower wishbone, and where the front was push rod and the loads were going this way, the rear end is pull rod. So we connect from here, and this link here is the pull rod. So rather than pushing up, we're now pulling the other way.
But why go pull rather than push? Well, there's actually no benefit regarding the suspension directly, but it's more about how things fit together.
The main reason will be a packaging perspective. So from an aero point of view, they want to keep the top of the gearbox as clean and as clear as possible to let all the air out. So by sending it that way, that works quite nicely. The one problem with a pull rod is then trying to make sure you've got enough space for your floor. So with push, if you're going from out here to up there, you've got all the space in the world for your diffuser to go.
Yeah.
But likewise, you've got all of this mechanical stuff up on the top that ideally you don't really want up there.
Right. So you're trying to package, or
you're balancing packaging against aerodynamics, I guess.
Okay, so once the load has gone through the push rod, it moves into what's called the rocker. It's basically a titanium piece with a few prongs coming off it to connect to the torsion bar, the damper, heat spring, and the anti-roll bar.
So this is a torsion bar or a spring, your traditional coil spring that you would squash this way. In this case, we have a spline at each end here and here, and we're trying to twist that to try and get torsion up and down here. So we can change how stiff or soft this spring is by how thick our material is, how long our tube is, and how much leverage we apply to the end of it.
But why use these torsion bars instead of traditional springs? Well, again, it all comes down to the packaging, making everything fit into the smallest space possible.
A coil spring can be quite a cumbersome thing. To get something really, really stiff, you need really, really thick springs. So from a packaging point of view, these are much neater. And also, I have a feeling these are better, more controllable in what we want them to do.
And these torsion bars might look simple, but they're a perfect example of F1 engineering, taking something as basic as a spring and reimagining it to save space and weight. Although, to be fair, they're not that forward thinking. VW Beetle used torsion bars in the 1930s. So next up are the dampers.
You've got dampers in here, like traditional corner dampers if you like. So you can see the gold stanchions here and here.
Yeah, you just mentioned the dampers down here. They're absolutely tiny.
They are tiny.
And they kind of come out across here and I suppose go into the side of the tub.
Yep, they connect here.
Connect down there.
There and there.
Yeah.
So instead of having the damper inside the coil spring, like in most race cars, F1 teams do something different. And again, this is all to do with packaging. The damper can simply sit more cleanly in this area. And interestingly, unlike other race series where teams constantly adjust their dampers throughout a race weekend, F1 teams will typically swap the entire damper unit for a different one if they need a different setting. This shows you the incredible lengths teams go to save weight. Why add the extra metal needed for the adjuster when you can just change the entire thing?
We have a rack of them, so no, we don't adjust them. We have a preset range, and then usually it's set by the vehicle performance group from here to say, based on data, this is where we think we want to go.
But Andy went on to tell me that in fact, they don't tend to change the damper settings too much.
That's kind of interesting for me to hear, because in the lower formula, when you're racing a thing, you've got adjustable dampers and you're changing them mid-session, right? You're doing it all the time, but I suppose your simulations are so good that you can kind of estimate that much easier.
And also, we have quite little trouble. The cars are quite low to the ground, the actual trouble involved. So a damping rate, while yes, it can make a huge difference, that will probably make you a bigger change to the car.
What Andy's referring to here is the heave spring, and that's really interesting. By the way, if you want to learn directly from F1 engineers about vehicle dynamics, aerodynamics and suspension systems, join the waitlist for our Driver 61 educational programs taught by actual F1 engineers. Link below. So what exactly does the heave spring do? Well, the faster the F1 car goes, the more downforce it creates. Literally thousands of kilos pushing down on the car. And if you only had the normal springs and dampers, the car would just push itself into the ground and destroy the floor. However, if the normal springs were stiff enough to hold the car up, it'd be so stiff that it would be difficult to drive quickly. Something I've experienced myself on the older F1 cars.
I've driven some early F1 cars that didn't have, you know, a third damper or a heave.
Yep.
And they're incredibly stiff.
Yep.
Right. So it means that they've got the same kind of stiffness in the straight or in the quick corners.
Yeah.
But then in the slow corners, they're horrible to drive because on all the bumps like this, got no traction.
Curbs are awful.
Yes, exactly.
And that's where the heave spring comes in. It's F1's clever solution to managing these massive aerodynamic loads while staying supple enough in the slower corners.
We want to run the car generally as soft as we dare when we're turning, whereas when we're in a straight line and we've got however many 100 kilos of downforce, a soft car just runs itself into the tarmac.
Instead of traditional springs or torsion bars, the heave spring uses something quite unusual: small donut-shaped wire meshes. These act as hard springs and a stop, preventing the car from dropping too low when it's got lots of aerodynamic force. And the teams do tune these from circuit to circuit. They adjust the gap, essentially how much the car can move down before these springs come into play.
So if you've got a very high-speed circuit, you might want to close the gap up because you've got a longer straight to give the car, it's got more aero for longer.
Yeah.
Maybe on a Monaco, for example, you've got a really bumpy circuit that isn't particularly high speed.
Right.
So you give yourself a bigger gap to give yourself a softer car for longer.
And finally, we have the anti-roll bar. On your road car, the anti-roll bar will usually be a metal rod bent into a U shape. It runs across the width of the car, with each end connected to the suspension on opposite sides. When one wheel goes up and the other goes down, like in a corner, the bar twists, resisting this movement. This reduces body roll, keeping the car flatter in the corners. But when both wheels hit a bump together, the bar doesn't twist at all, so it doesn't affect the car's ride comfort. And aside from the comfort, the objective is the same in an F1 car: to keep the car flatter. However, the packaging again is a little different. The roll bar still twists a bit of metal, but on the Alpine, this goes down the centre of the main torsion bar and is held at the bottom against the tub. But it works exactly the same, albeit taking up way less space. If you enjoyed this video, check out the other videos I made with Alpine. Thanks again to Alpine for the incredible access. If you enjoyed this video, please consider subscribing, and I'll see you next time.